This lecture is about cut elimination. In the previous lecture, we developed this sequent calculus, which is a new formulation of a propositional logic based on this notion of a sequent, gamma arrow C. Now it's time to analyze its meta properties. And we will look at a property called cut elimination. And the story goes as follows. Earlier in this course, we developed this natural deduction system for propositional logic, where we use this hypothetical judgment. And after formulating this system, we had to revisit this system and analyze its meta properties. In particular, we wanted to convince ourselves that this system is okay, sound in some sense. So the first step was we tried to prove this reflexivity and substitution theorem. So this substitution theorem is stated like if gamma turnstile A true and gamma A true turnstile C true, then we have gamma C true. So we have to prove this substitution theorem before proceeding further, because if this substitution theorem fails, then this system is basically nonsense that does not obey the usage of this turnstile symbol. So this was the first meta property that we had to verify ourselves. And this is essentially lemma's theorem. So in the course of reasoning, we first prove A true, and afterwards we use this A true as if it was a part of the original assumption. So we may assume that here in this step we prove this A true as a lemma, and in proving this hypothetical judgment, we use this A true as a lemma, whose proof has been established before. So in the case of a natural deduction system based on this hypothetical judgment, we had to verify this substitution theorem. If this substitution theorem fails, then this is a total nonsense. And basically, we are going to repeat the same story, this time for sequent calculus. In the case of sequent calculus, gamma arrow C, we have to prove this cut elimination. But first, but we will actually start with this admissibility of the cut rule, which is stated as follows. If gamma arrow A and gamma A arrow C, then we can conclude gamma arrow C. So this statement is called admissibility of a cut rule. Later, we will actually introduce another rule called the cut rule and show that this cut rule is admissible. So what that means is that even adding this cut rule to the system, so this is the original sequent calculus, and we are going to add another rule called the cut rule. But this rule, cut rule, is admissible. So adding this cut rule does not actually increase the expressive power of this sequent calculus. Or in other words, adding this cut rule does not change anything at all in this sequential calculus. And this statement, admissibility of a cut rule, resembles quite a bit like the previous substitution theorem, although the interpretation is very different. Remember that this is interpreted as a up arrow, but this is not interpreted as a hypothesis, although hypothesis is a particular case of neutral judgment. So, strictly speaking, this is a down arrow. But superficially, these two theorems, this substitution theorem and this admissibility of a cut rule, the two statements look quite similar. So in order to show that this sequential calculus is sound, that is, this sequential calculus correctly uses this notation, sequent. In order to verify this property, we have to first show that the cut rule is admissible. That's the first step. If this property doesn't hold, this sequential calculus is nonsense. Just like if a substitution theorem fails, the whole natural deduction system is nonsense. So that's what we have to first prove. So let me write the admissibility of cut rule again. Admissibility of the cut rule. It says if gamma leads to A and gamma A leads to C, then we can get rid of this A, gamma right arrow C. So let's look at what this statement means. So according to our definition of this sequent, the first sequent can be interpreted as we have gamma down arrow, and then we can prove A up arrow according to the definition of this notation sequent. So we have some inverted, we have this hourglass. And what's the meaning of this sequent? This sequent means in the presence of a gamma down arrow and A down arrow, we can prove C up arrow. Now let's imagine that for some reason, we allow this normal judgment can be converted to this neutral judgment. For example, we could introduce a new conversion rule, another conversion rule, which converts A up arrow normal judgment into down arrow neutral judgment. So we could call this rule up arrow, down arrow. Remember that the coercion rule converts down arrow into A up, down arrow, the neutral judgment into up arrow, normal judgment. And this rule is typically found in the middle of this hourglass shape. But this time, suppose that we allow this normal judgment to be converted to this down arrow, neutral judgment. Then, thanks to the second sequent, now we have gamma down arrow and A down arrow. So therefore, we can complete the proof of C up arrow. So the if phrase, the if part, allowed us to make this assumption. Again, notice that here we convert up arrow into down arrow. Normal judgment is converted to neutral judgment, not the other way. Then, this admissibility of cut rule allowed us to deduce this one, gamma down arrow leading to C up arrow. Oh, let me read this one. So if we have these two sequences, we can imagine that there is the first part of the proof and the second part of the proof. At the conclusion, this then phrase means that we can construct this proof, C up arrow from gamma down arrow. So what that means is that according to this admissibility of cut rule, we can always get rid of this one. So informally speaking, this admissibility of a cut rule allows us to get rid of all instances of this rule, the application of this rule. And this one basically converts a up arrow into a down arrow. And this is precisely where detour occurs. Recall that detour is basically intro followed by elim. And we can imagine that this is up arrow, so perhaps we have an instance of some introduction rule here. And this is down arrow, so we have perhaps an application of an elimination rule here. So this is precisely the pattern that we observe in every detour. So this is basically detour. So this one says, so now this admissibility, what this admissibility says is, if you have a proof that involves a detour, then you can get rid of it. You can deduce the same judgment without using detours at all. That's what this admissibility of a cut rule states, informally speaking. Now we can see why this property is almost equivalent to global soundness. So recall that this local soundness basically local soundness states that if you have an introduction rule followed by elimination rule, you can get rid of it. Get rid of this detour. But in the statement of this local soundness, we had to consider every logical connective. For example, we consider implication introduction followed by implication elimination. We can get rid of this with this beta reduction. Beta reduction, basically it's a function call. And we also had to consider this case. Conjunction introduction is immediately followed by conjunction elimination. And we show how to get rid of this. And similarly, we show that this disjunction introduction rule followed by disjunction elimination rule. How can we get rid of this? So in the proof of local soundness, we had to consider every combination of introduction and elimination rule for every logical connective. We had to visit every logical connective one after another. So that's what this local soundness states. But this time, this admissibility of cut rule is much stronger because essentially what it tells us is you can remove this one, up arrow converted to down arrow. But this is precisely where detour is found. And this statement does not say anything about the form of A. It doesn't say anything about A is implication, conjunction, disjunction. It doesn't tell anything about the particular form of this formula A. So what that means is that I don't care about the shape of this detour. So whatever detour it is, I can get rid of it, irrespective of the particular form of this formula A. So in that sense, this admissibility of a cut rule says I can remove any detour, or it's globally sound. because you don't care about the form of this detour, because it allows us to remove any detour. In contrast, in the study of this local soundness, we had to consider specific combinations of introduction rule and elimination rule. In this regard, we can say that this admissibility code rule is almost equivalent to global soundness of the logical system. And as a direct consequence of this admissibility of code rule for global soundness, we can easily prove bottom true is not provable. So that's our ultimate goal. Bottom true is not provable in this system. Now let's try to prove this admissibility of code rule. So I'd like to show the key idea in the proof. So the statement is if gamma arrow A, let's say this proof is called D, and gamma A arrow C, let's call this proof E, then we have gamma arrow C. And let's call this proposition A as code formula. So remember that in the study of sequential calculus, we prefer this terminology formula to propositions. So that's the reason that this proposition A is usually called a code formula rather than code proposition. So A is called a code formula because informally, we'd like to cut this one and cut this one and then produce this one, this new one. So this formula is best called the cut formula because we are going to cut it away. And the proof proceeds by triple nested induction. It's not just a double nested induction, it's a triple nested induction. And the ordering in applying this nested induction is significant. First, we analyze the structure of cut formula A itself. And next, we consider the structure of the proof D for gamma arrow A. And next, we consider the structure of this proof gamma A arrow C. So what this thing means is that, let's just say we have another pair of sequence, say gamma prime arrow A prime and gamma prime A arrow C prime, gamma A prime C prime. So we have these two sequences where A prime is a subformula of A. So A prime is strictly smaller than A. It's a subformula of A, so it's strictly smaller, or a subformula of A that is strictly smaller. So for example, A could be A1 implies A2, and A prime could be just A1. In this case, we can immediately apply induction hypothesis on this one and deduce. So basically, we can cut away this A prime and deduce gamma prime C prime. And the reason here is that A prime is strictly smaller than A. A prime is a subformula of A, so A prime is strictly smaller than A. So you don't even have to consider the structure of the proof, this one, and this proof. In other words, the second and the third cases do not apply at all, simply because the cut formula is strictly similar. So that's what we mean by the first case in this triple nested induction. So basically, if you have these two sequences, that match the pattern in this statement, where the cup formula is something smaller, then you can apply the induction right away. Now let's consider the second case. In the second case, the cup formula is the same. So for example, we might have something like gamma prime right arrow A and gamma prime A arrow C prime. So this time we'd like to cut away this one and produce a new sequence gamma prime arrow C prime. But this time, this formula, cup formula, is the same as this one and this one. The two cup formulas are the same. So you cannot apply induction for the first case. But suppose that the first sequence, its structure is strictly smaller than the proof of this sequence. So for example, suppose that this one was gamma A, and in the premise we have gamma prime arrow A. Now let me get rid of this. So the proof D looks like this one. The conclusion is of course gamma arrow A, so this one. And the premise has this sequence, gamma prime right arrow A. Now the proof of this sequence is strictly smaller than this one. So therefore, thanks to the second case in this nested induction, we can apply induction and generate new result. So basically, if you have this one, you'd like it to apply cut on this sequence and this sequence and get rid of A and produce gamma prime arrow C prime. And this is acceptable. This is accepted because the proof of this sequence is strictly smaller than the proof of this sequence. So even though the cup formula is the same, because this proof is smaller than this one, the structure of this proof doesn't matter. So we can ignore this case, and we can obtain this sequence. That's the second case. And finally, what about the third case? In this case, the cup formula is the same, and the first sequence has precisely the same structure, but the second proof is strictly smaller. So what that means is that we have something like this. For example, we have gamma right arrow A and gamma A right arrow C. So suppose that this is a proof D, this is a proof E, and let's say the premise contains something like gamma A C prime, for example. Now, the cup formula is the same, it doesn't change. And the proof of the first sequence remains the same. But the proof of the second sequence is strictly smaller than this proof. So therefore, we can apply induction on the same cup formula and the proof of this sequence, and the proof of this sequence. This is the same, but this is strictly smaller. So as a result, we can apply cut elimination here and here to obtain gamma arrow C prime. I have illustrated how to apply induction, how we can, in which case we can apply induction. And I'd like to show two important cases in the proof. So let's try to prove this cut, the admissibility of a cut, gamma arrow A and gamma A arrow C, then gamma arrow C. So this is a proof D and this is a proof E. And there are quite a few cases in the actual proof of this admissibility of the cut rule. And I'd like to highlight the proof with the two representative cases. In the first case, we focus on this formula. So on the first sequence, we focus on the cup formula. And in the second sequence, we also focus on the cup formula. So in this case, D is going to be something right rule, and E is going to be something left rule. And let's consider the representative cases, which is implication. So the case goes gamma arrow A implies B, and we focus on this formula. So this is going to be implication right rule. And this one, this is D, and this is E. And this time we have cup formula is A implies B, arrow C. And this time we focus on this one. So this is the cup formula. This is the cup formula. And the premise of the first sequence is gamma A arrow B, and here the premise goes gamma A implies B leads to A, and the second sequence in the premise is gamma A implies B leads to C. Okay, so that's the assumption. Now let's try to find out pairs of sequence where we can apply this cut elimination. First, we can apply cut this one on this one. So what I mean by this is we pair this sequence and this sequence and apply cut elimination. So the cut formula is going to be A implies B is the same. And the first proof is gamma A implies B. It's also the same. But luckily, the second sequence has proof that is strictly smaller than the original one. So this one is strictly smaller than this one. So therefore, we can apply induction hypothesis on the same cup formula, the same first proof, but strictly smaller proof of the second sequence. So by applying this induction hypothesis, we can cut this formula away and obtain gamma right arrow A. So basically we pair this sequence and this sequence. Now let's pair this sequence this time, this one. And it looks like we can apply the induction hypothesis on this sequence and this sequence because here we have A implies B on the right-hand side of the sequence. And here we have the same formula, A implies B, on the left-hand side. So the plan now is we'd like to apply induction hypothesis on the same cut formula and the same sequence, the first sequence, and the second one is gamma A implies B, B arrow C. But the problem here is the left side, the set of formulas on the left side is different. Here we have gamma. Here we have gamma B. So it doesn't match the pattern that is expected in the application of this admissibility of a cut rule. We have something like gamma arrow stuff, some stuff, and gamma, actually this is a cut formula. Let's say this is the cut formula. This cut formula. Then we have to have something like this one. Then we can eliminate this cut formula and produce gamma arrow C. But this set of cut formulas, this gamma and the gamma B, do not match. So as a trick, we have to, from the proof of this one, this is the original proof, D, and we'd like to weaken, and then produce gamma B arrow A implies B. So this is, let's say, D prime. An important point here is this weakening does not change the structure of the proof at all. So what that means is that if D is a, so figuratively speaking, if the proof D looks like this one, then D prime looks exactly the same. You just visit every part of his derivation tree and then just add B, that's all. So even though this proof and this proof, the two proofs, D and D prime, are different, they have precisely the same structure. So what that means is that we can just assume that this one is essentially the same as this one. Now, we would like to apply induction on this one and this proof. This is the same, the cut formula is the same. The first proof, the proof of the first sequence is the same, but luckily, the proof of the second sequence, this one is strictly smaller than the original one. This one is strictly smaller than the original one. Therefore, we can apply induction hypothesis again and then obtain this one. From this case, we basically cut this one away. So we obtain gamma B arrow C. So we considered this pair of a sequence and this pair of a sequence. Now it remains to exploit this sequence. We have to use this sequence somewhere, and we have to consume this sequence, the new one, and this new one. And the story goes as follows. First, we can pair this sequence and this sequence. So basically, so what we want to do is take this one, gamma A arrow B, and take this one, gamma B arrow C, and this time the cup formula is B. Now this cup formula B is subformula of the original cup formula A implies B. So the structure of this proof and this proof doesn't matter because the cup formula B is strictly smaller. And this case precedes the other two cases. So the structure of D doesn't matter because the cup formula is strictly smaller. So now you apply induction hypothesis on cup formula B and this new sequence D and this new sequence, and then obtain, basically you cut it away. So I was confused and took a wrong case. So the plan is we would like to apply cut elimination on this one and this one. And then perhaps we would create gamma arrow B. And then we apply cut elimination again on this one and this one. And then we produce gamma arrow C. So the story is now we'd like to take this one and this one. So now we have gamma arrow A from here. And we take this one, the premise, gamma A right arrow B, the premise. And this time the cup formula is A. So because the cup formula is a subformula of the original cup formula, namely A implies B, we can apply induction hypothesis on this cup formula and these two sequence. And the proof of this sequence don't matter at all because the cup formula is smaller. So from this one, we obtain, basically we cut it away and then obtain gamma arrow B. Now we combine this one and this one with the cup formula B. So cup formula is B. We have this one and we have this proof. And then apply induction hypothesis and we obtain C. So we complete this case. The next case is so the next case looks like, so we have gamma right arrow A and gamma A arrow C. But this time, instead of focusing on the formula A here, we'd like to focus on somewhere in gamma. So for example, this gamma could be gamma prime B1 implies B2. And instead of this cup formula, we'd like to focus on B1 implies B2 on the left side. So this one is going to be implication left rule. And in this case, the shape of this derivation tree doesn't matter. Whether we have left rule or right rule, it doesn't matter. So let's consider this case. So now this time, this is gamma prime B1 implies B2 and A implied C. So we have some proof. And the premise goes gamma prime B1 implies B2 arrow B1, and then P1 implies B2, and we assume B2, and then leads to A. That's the result of applying implication left rule. Now, how can you apply this cut elimination? We have to find a pair of sequence. And in this case, if you think about this case, this one and this one can be paired because that's the only pair of sequence actually where the cut formula is found. So we'd like to apply induction hypothesis on formula A. So this time cut formula is the same. And the first sequence is gamma B1 implies B2, B2A. This is the first sequence. And the second sequence is this one, gamma prime B1 implies B2, A arrow C. But the problem here is, it's the same problem. The left side of this sequence doesn't match the left side of this sequence. So this sequence here, B2 is missing. So what we do is, similar to the previous case, we weaken it. And then we have gamma prime, B1 implies B2. We weaken with B2 and A arrow C. So we have added this new formula. And the key and important point here is, even though this sequence is different from this sequence, the proof structure is precisely the same. So for example, if you measure the size of this proof, the proof of this sequence, then the size of this proof is exactly the same. Now we can apply induction hypothesis on the same cut formula. This is the same. But this proof is strictly smaller than the original proof. So actually the size of this sequence doesn't matter because this is smaller anyway. So now from this case, we basically cut away A, and then we obtain gamma B1 implies B2 arrow C. So we have produced this one. And the plan now is we'd like to rebuild this rule, but by replacing A with C. So if we manage to replace this A with C, this would be converted to C as well. And that's what we want. So the way that we construct it is make a copy of this one. Gamma prime B1 implies B2 for B1. And then carry it over here. Gamma B1 implies B2, B2, C. And then apply implication left rule again. And then we obtain gamma prime B1 implies B2 arrow C. So we just replaced this formula with C. So that's the second example that we'd like to consider in the proof. Now, suppose that we have finished the proof of this admissibility of a cut rule. And so we have admissibility of cut rule. So it says, if gamma arrow A and gamma A arrow C, then we have gamma arrow C. And this leads to another conclusion called cut elimination. So perhaps the cut elimination is the most important theorem you will find in the study of proof theory. It's one of the central theorems in the study of logic. So in every formulation of logic system in proof theory, you will see cut elimination, because without cut elimination, the system is basically not sound. So this is the required step to use, the required step before using your proof theory. You have to first formulate the sequential calculus, and prove cut elimination. And this admissibility, in the statement of admissibility of cut rule, the cut rule is actually this one. Suppose that we have this sequence calculus, gamma right arrow A, and now we add a new rule for the cut rule. So this cut rule is gamma arrow A, gamma A arrow C, then you deduce gamma arrow C. This is a cut rule. So basically, that's what this admissibility of a cut rule says. And I'd like to show that this system, the original system, extended with this cut rule, is equivalent to the original system itself. So that is, this cut rule, it doesn't matter. The expressive power of this system does not increase or does not decrease even with the addition of this cut rule. You add this cut rule, but system doesn't change because this rule is basically admissible. And with this result, admissibility of cut rule, we can show the equivalence. If we can show the equivalence, this cut is redundant, so we can eliminate it. So that's where this terminology, cut elimination, the name of the theorem, cut elimination, comes from. Let's. The proof is actually trivial, and the plan is, let's say we use a new sequence, arrow plus, in this extended system. So in this extended system, we use this new form of sequence. And the original system used this one. And cut elimination basically says gamma right arrow A plus if and only if gamma right arrow A. So what this thing means is that it doesn't matter whether you have this cut rule in your system or not. Even without cut rule, you lose nothing because adding this cut rule back does not bring anything new. These two systems are equivalent. And it's pretty easy to prove this one once you have this admissibility of cut rule. So the crux in the proof of cut elimination is actually to show the admissibility of a cut rule. And it's almost like a corollary to the admissibility of a cut rule. So this is the most significant, the most important theorem you can find in the study of proof theory.